with this, I'd like to introduce our first speaker, but before I do that, I've got a tiny little confession to make. Recently, I've seen a beautiful photo of myself. I know why you're laughing. It does sound absurd, thank you. Because after all, I've got a face for radio, right? But this photo was indeed beautiful, and there was a reason for it. It was enhanced. And by enhanced, I mean photoshopped. And by photoshopped, I mean photoshopped beyond recognition. And the reason I'm mentioning this is that, well, our first speaker today, Sean Parent, he's a principal scientist and software architect for Adobe Photoshop and also mobile imaging applications. He's been with Adobe since 1993, when he joined as a senior engineer working on Photoshop, and later managed Adobe's software technology lab. Sean spent a year at Google working on Chrome OS before returning to Adobe, and earlier he worked at Apple, where he was part of the system software that developed the technologies allowing Apple's successful transition to PowerPC. And today, the talk is called Generic Programming. Let's have a big hand for Sean Parent.
Hey, thank you. And thank you so much for turning out after the mid-party. I know that was probably difficult for some of you, a little difficult for me. I was there way too late. This year marks the 30th anniversary of an important event. So this talk is a little unlike many of my normal talks because I thought it was important to recognize this event. So this is a bit of a history talk, but I'm hoping all of you are going to find it interesting. This is a quote from Alex Stepanov. You cannot fully grasp mathematics until you understand its historical context. So what happened in 1988? Anybody know? You know, it's the title of my talk. You guys should know, right? So this paper was published. This is where the term generic programming was coined. The term first appeared in a paper the year before, but it was actually a forward reference to this paper that was in the process of being written. So I count 1988 as the year when generic programming was invented, if you want to call it invented. There's two authors on this paper. This is David Musser. So he was a professor at RPI, and he was collaborating with Alex Stepanov. That's a picture of Alex when Alex worked with me at Adobe. I like that picture. The papers behind him are copies of an old Euclid manuscript. So Alex and Dave collaborated on this paper, but the history doesn't quite start there. But let's give the definition of generic programming that was given in the paper. So by generic programming, we mean the definition of algorithms and data structures at an abstract or generic level, thereby accomplishing many related programming tasks simultaneously. The central notion is that of generic algorithms, which are parameterized procedural schemata that are completely independent of the underlying data representation and are derived from concrete and efficient algorithms. So that's the definition of generic programming. I think that still holds up today. But let's go back in time a little further. Right, let's see what happened in 1976. This is going back in time a little too far. That's a picture of Alex a little before 1976. So in 1976, Alex was a computer scientist, a programmer, and he had a job interview to work on a system in Russia having to do with parallel computation. And Alex had never done any parallel coding, any threaded coding of any kind. And so he's trying to prepare for this job interview, and he's thinking, what does it mean to execute code in parallel? And he actually got food poisoning the night before, and so he ends up with a fever, and he's sick. And during this time, he realizes that there's a relationship between parallel computation and the associative property, right? That in order to do parallel computation, you need to be able to reorder the computation. So, put another way, parallel reduction is associated with a monoid, right? A monoid is a set that's closed under an associative binary operation and has an identity element, right? So what Alex saw here was that programming had some relationship to algebraic structures. Okay? And Alex was a mathematician, so he just filed this notion away. He actually didn't get the job. So he starts thinking, though, that software is associated with algebraic structures. In 1977, this paper was published. Alex said he read this paper in 1979, so a couple of years later. This is John Backus. How many people here know who John Backus is? Wow, okay, 2 hands maybe. This is a name that you should know as computer scientists. So John Backus created Fortran. John Backus, if you know of BNF, Backus-Naur formalism, he's the Backus in that, which is how you describe programming languages. He's a Turing Award winner, right? This is his Turing Award lecture from 1977. And in this, he proposed a language, FP, which very much popularized functional programming. He didn't invent functional programming, but this paper, I think, very much brought it to the forefront. So Alex reads this paper, and John Backus in this paper talks about functional forms. And he talks about the fact, well, in this paper, he talks about having 5 functional forms with which you can build up kind of all the rest of the computational infrastructure. So he reduces everything to these 5 functional forms. And Alex looks at this and he realizes that these 5 functional forms, if you were talking about them in terms of mathematics, these would be theorems. Okay, you have a set of axioms and you have a theorem. And he looks at this and he says, this isn't quite right? You don't just have 5 theorems in mathematics, right? You have an infinite number of theorems in mathematics. And so taking this pure reductionist view, he thinks is going a little too far. Another paper that he reads the same year, 1979, is Ken Iverson's Turing Award lecture. Who here knows the name Ken Iverson? 1 hand over here. Okay. Wow, you guys need to go read the Turing Award papers. Just go start from the first Turing Award, read all the lectures. They're all brilliant papers, worth your time. So Ken Iverson, he's the creator of a programming language called APL. Right? How many people here have seen or heard of APL? Okay, a few more hands. This was interesting because I gave this talk a few weeks ago inside of Adobe, and I asked the same question, and not a single hand went up. And I'm kind of old enough that I wouldn't know how you could not have seen APL. Again, that's what Ken Iverson looks like. So this is an APL program, right? This is Conway's Game of Life written in APL. Okay, so it looks a little foreign. At the time, in the 1970s, if you were to write this, you had a custom keyboard so that you could type the symbols, okay, so that you could express a program. So this is fairly dense. I don't know enough about APL to explain the whole thing to you. I do know the plus followed by a slash is a sum. I do know the little circles are doing matrix sorting. The circle with the horizontal is sort by row, and with the vertical is sort by column. But honestly, I don't remember enough APL to decipher this. But this is what an APL program would look like. But Ken Iverson's primary thesis here was that notation was a tool of thought, that we should write code as we write mathematics, and how we write code and how the code looks matters. So that's the key takeaway. So in 1981, Alex has left the Soviet Union. He is now in the US working for GE Research, and he collaborates with Dave Musser. This is where their collaboration starts, and Deepak Kapoor. This is a picture of Deepak. And they work on this language, which starts to sound like generic programming again here. We've got a language for manipulating generic objects. But this is not what you would think of as a traditional programming language. So Tecton is a formal methods language. It's a proofing system using abstraction and specialization as the key structuring mechanisms for proving software correctness. Okay, so it's a language that you use to machine prove program correctness. Dave Musser continued to work on Tecton for years after this at RPI. So you can go, there are many papers written on Tecton. You might even be able to find an implementation or two online. So that came about. So in 1986 and 87, Alex collaborates with this individual. So this is Aaron Kirschenbaum, and again, Dave Musser, on a couple papers around higher order programming. Now these papers are written in Scheme, and so it's a functional programming approach. And how many people here at least have heard of Scheme? Okay, we're getting a little more modern. People are catching up. Aaron Kirschenbaum there is a great computer scientist. And he convinces Alex that functional programming kind of isn't all it's cut out to be, that you can't ignore arrays, okay, and you can't ignore mutation if you want efficiency. So that brings us up to 1987. Alex works briefly at Bell Labs in 1987. Where he meets this guy. He starts a friendship with Bjarne Strustrup. Okay, so they work together at Bell Labs, and they have a great friendship ongoing still today. He also meets this guy, Andrew Koenig. How many people here know who Andrew Koenig is? Okay, quite a few, right? ADL, argument-dependent lookup, is also known as Koenig lookup. Andrew, I don't think, appreciates that because that's not quite what he was going after with ADL. But Andrew explains to Alex the beauty of the C machine, right? Up until this point, Alex kind of viewed the C machine as a hack, right? And Andrew's like, no. The C machine is this beautiful mechanism that maps very well to actual hardware. And it's got a bunch of amazing properties. Not the least of which is the fact that it exposes all of memory to you, right? That it treats memory as if it were just a large array of bytes and you can access anything. And that's not a hack, that's a beautiful representation of how the machine actually is, right? And although Alex doesn't work directly with these two guys, he reads a lot of their code. They were both at Bell Labs at the same time. So this is Ken Thompson and Rob Pike. Both of them are now at Google. Ken Thompson, how many people here know the name Ken Thompson? Quite a few people, right? So Ken Thompson is the father of Unix, right? There was a project at Bell Labs for something called Multics, and Ken took that and turned it into Unix. He held the title of the author of a chess program that wiped out kind of every other chess program at the time on the planet. He is the inventor of the UTF-8 encoding, so if you've ever heard of UTF-8, that is Ken Thompson. Rob Pike worked with Ken on Unix and then on Plan 9, which was to be a successor of Unix, an operating system very much structured around pipes, never quite took off. Now the two of them collaborate at Google and created the Go language, right? So you might have heard of Go. I think there's some talks here on Go. So Alex reads their code, specifically their code for Unix and Plan 9. He finds this is really beautiful code, right? This code is written in C, and it is just, it's just amazing, just very clean. So something else happens in 1987. Alex discovers this guy. This is Leonhard Euler. How many people know the name? Hey, okay. Some folks who have a better education than I had at the time. So Euler is an 18th century Swiss mathematician. He's a physicist, astronomer, logician, and an engineer. And reading Euler changes Alex's perspective on mathematics, right? Alex refers to it as Euler de-Borbicized him. How many people here know the name Bourbaki? Nah, not so many. You kind of should know the name Bourbaki. Bourbaki refers to Nicholas Bourbaki. Nicholas Bourbaki is not actually a person. It is a pseudonym for a group of people, a group of French mathematicians who formed the Bourbaki Foundation in the 1950s with the goal of basically rebuilding mathematics from first principles. I have to put in a correction here. Somebody sent me an email last night objecting to something that I had said, which was that Bourbaki was responsible for set theory. And I think that's a misleading statement. I don't mean to imply that Bourbaki invented set theory. That would not be a true statement. But Bourbaki is responsible for popularizing set theory. If you're my age, you would know the term new math. This was math that you learned in kind of secondary school. And you would take your homework home, and your parents were like, "What is this? I do not know what this math is. This is not the math my parents learned in school." The reason for that is the math my parents learned in school was rooted in geometry and in Euclid. And in the 1950s, Bourbaki wrote this very large set of volumes kind of rebuilding the fundamentals of mathematics, and that became popularized in schools as a new way to teach mathematics. And so mathematics, instead of being rooted in geometry, became rooted in set theory. So the email I received last night was somebody who objected to me saying that Bourbaki invented set theory. They also kind of objected to the relationship between what Bourbaki called set theory and what you would think of as modern set theory now. I'm not a set theorist, so I'm going to make no claims about that, but I also don't want to be misleading. So what does it mean that Alex was de-Borbicized? So it means his thinking about mathematics shifted from one where you're thinking about mathematics as invention, as you invent a set of rules, logical rules, and you carry out the set of rules, and that lets you create large systems, to one where mathematics is discovered, that mathematics is rooted not in abstract thought, but it's rooted in precise quantitative laws, that mathematics is rooted in physics, okay, not in abstract logic. So Euler was one who thought that knowledge is founded on the basis of precise and quantitative laws, and that's where mathematics stems from. Mathematics is discovery and not invention. And this changes Alex's thinking a bit, right? To say that, no, software, it's not that there's a relationship between software and algebraic structure, it's that software is defined on algebraic structure. Are all software, correct software, incorrect software, it's all defined on top of algebraic structures. And that it's our job to discover what the algebraic structures are that rule software, right? Not a process of invention, but a process of discovery. So that brings us back up to 1988 and the publishing of this paper. Right? Now you might think that this paper would be published in C++, right? Alex worked at Bell Labs, but a lot of the work on this paper actually happened before Alex had gone to work at Bell Labs. And how many people recognize the language here? A couple people. Yeah, more than a few. That's pretty good. How many people thought it was Pascal? Nah, you're all wrong. So no, this is not Pascal. This is Ada. Okay, we'll blow it up a little bit here. So this is the code. The paper develops a partition algorithm in Ada. So it looks somewhat like an STL algorithm in its interface. We've got an in-sequence pair of coordinates, F and L, first and last, which are a little like iterators. It's going to have an out coordinate, which is the midpoint on partition. Does everybody know what partition does? Right? Okay, to explain partition to you, partition takes a sequence and a predicate. The predicate determines whether or not an element in the sequence is a good guy or a bad guy. And it reorders the sequence so that you have all the good guys followed by all the bad guys. And it returns the point between them. Okay? So that's what partition does. There's a partition algorithm in STL. It's a very useful algorithm. There's actually several partition algorithms in STL. So there's this extra parameter here, middle OK. It's an output parameter, and it's a Boolean. Anybody have a guess as to what middle OK would mean? Nobody? Which set the middle element belongs, whether the middle element is a good guy, in which case it would be true, or the middle element is a bad guy, in which case it would be false. The reason why you need this extra Boolean is because the coordinates for our range here, it's a closed range. Okay? So we have no way to express off the end, and that creates a problem. Right? The partition point could be at any position within that range. And so you might have a partition point at the end, and does that mean that that end element is in the set or not? So you have this additional parameter. Okay. This code is not particularly well parameterized. This is the predicate here. It's a global function called test that works on coordinates in the sequence. So we can sort our sequence into good guys and bad guys, but it's not parameterized on what the actual predicate is. Right? We do see other familiar items like swap, right? You'll see swap in STL. And Alex worked on a fairly large collection of algorithms like this for Ada and published this book with Dave Musser. Right? So the Ada generic library. So this is very much a precursor to the STL. Now we're spinning around here because we're going to a little bit of an alternate universe, right? So while Alex is doing this, I'm working at Apple in Apple's System Software Group. I'm aware of Bjarne Strustrup's work. I have his book. This is my copy. Shot that picture on my desk of the first edition of the C++ programming language. It's a beautiful, thin little book. Does not look much at all like what you would think of as the C++ programming language. It's written in the style of K&R. So I'm working at Apple. I'm working in the System Software Group. I'm actually not writing C++ at this time. I'm writing in C. Prior to writing in C, I had written primarily in Modula 2 and Object Pascal. I worked, like I said, in the Macintosh System Software Group. This is my copy. Again, that's my desk in the background there of a preliminary edition of Inside Macintosh. This is known as the telephone book edition of Inside Macintosh. So this was the documentation for the Macintosh System Software before it was kind of formally published. So it was published like a telephone book. on very thin paper. You can see I read it in reference. Okay. Am I back? I'm back. Okay. So this is inside Macintosh, and I'm working inside the printing and graphics group. This is the QuickDraw chapter. That's the graphic system for inside Macintosh. One of the first things I did was I worked on part of the QuickDraw system, which is known as regions, which is a way to describe an arbitrary shape and render an arbitrary shape within QuickDraw. So QuickDraw was created by this guy, Bill Atkinson. How many people here know the name Bill Atkinson? A few people. So one of the original guys on the Macintosh system software team. He's also the creator of something called HyperCard, which was like this close to inventing the internet, but not quite there. There's a story about Bill Atkinson and regions. At one point, well, Bill was working on the original Macintosh. He had worked on the Lisa before that and QuickDraw before that. Bill was in a bad car accident. He was driving his Corvette to work, and he turned a corner too fast and went into the back of a truck and ended up in the hospital. And Steve Jobs at the time came to visit Bill in the hospital, and just as Bill was regaining consciousness and asked Bill, you know, is everything okay? Are you good? We're very worried about you. And the story is that Bill turned his head to Steve and managed to smile and said, "Don't worry, Steve. I still remember how regions work." Okay, so it's a good story, and it gives you some idea of how important regions were kind of viewed within the company, and they really are quite a brilliant piece of work. This is a quote straight from that page of my copy of Inside Macintosh. All grid coordinates are integers. So this is talking about the coordinate system for QuickDraw. All grid lines are infinitely thin. Right? This is somewhat a different view than what you typically see in graphics. So the grid here, the coordinate grid for QuickDraw, goes between the pixels. Okay, so a pixel is bounded on 4 sides by coordinates within QuickDraw. And Bill wrote these words: "These concepts are important. They mean that all elements represented on the coordinate plane are mathematically pure. Mathematical calculations using integer arithmetic will produce intuitively correct results. If you keep in mind that the grid lines are infinitely thin, you'll never have endpoint paranoia. The confusion that results from not knowing whether that last dot is included in the line." Okay. So what he's talking about here is a very fundamental principle, and that's that for any sequence of things, of n things, there's n plus 1 positions within that, right? So you think about the positions within a sequence as being between the items. This is the code that I worked on for regions. You can download this now from the Computer History Museum, so all the sources for QuickDraw are up there. How many people recognize this language? A couple people. So this is 68,000 assembly language. That's what the region code was written in. The work that I did on the region code was to remove many of the 16-bit limitations so that you could have larger regions if you had enough memory in a 32-bit environment. So I gave this talk a few years ago on, there's a section of my talk, it's my C++ seasoning talk, there's a section on it called No Raw Loops. And these days I find it somewhat amazing that nobody has ever commented on the way I represent sequences here, right? Right. To this day, I still draw pointers as being between the objects, not to an object. Okay. So this is an algorithm called gather, which is a pair of stable partitions in STL. So what that does, what this little piece of code does, is it takes all of the good guys, all of the green guys, the selected guys, and it moves them to a position P. So it's just a pair of stable partitions, right? So it does that, and it returns the result of the two stable partitions, which tells you where the new range is, right? So if you view the world this way, with pointers between elements, you have no ambiguity about what's inside your range and outside your range, right? There is no off by one paranoia that comes up. There's no middle okay parameter inside of your algorithms, right? So again, the fundamental principle here is that for a sequence of n elements, there are n plus 1 positions. Let's move forward a bit to 1993. So in 1993, I left Apple and I joined Adobe to work on Photoshop at the time. I have not worked on Photoshop for that entire time. I've done a lot of things in my career, even though I'm back on the Photoshop team now. At the same time, Alex resumed his work on generic programming, and Andrew Koenig, his friend from Bell Labs, suggests writing a standard library proposal. Okay. And so in 1994, this happens, the standard template library. Okay. There are two authors of the standard template library. One is Alex Stepanov, who we've already met, and the other is Meng Li. This is a picture of Meng. She's the one person here who I couldn't find a picture of her on the internet. I know there was a picture in an old interview in a Dr. Dobbs article of her and Alex. The only instance of that picture that I could find on the web was just the Alex half, not the Meng half. I thought that was somewhat insultive. I sent an email to Meng, and she was kind enough to send me a picture of her circa about this time frame, 94, 95 time frame. So that's a picture of Meng. Alex gives Meng a huge amount of credit in the development of STL. He will tell you flat out that the STL would not have happened without Meng's assistant in putting it together. So a beautiful piece of work. But let's back up one more time here, back to 1983, to understand a little bit about why this was a big deal. Why was the STL a big deal when it came out? So in 1983, this article was published in the ACM from John Bentley. That's a picture of John. John had a column in ACM called Programming Pearls. You can still find a bunch of these articles. You can find them online these days. There's also a book titled Programming Pearls by John Bentley that collects many of these articles into a nice book. And this article was on writing correct programs. So this is a quote from that article. I've assigned this problem. The problem he's talking about is a problem of doing a binary search. Okay, so he's got a description of a binary search as a problem in a class that he's teaching. He says, I've assigned this problem in courses at Bell Labs and IBM. Professional programmers, right? These are not run-of-the-mill programmers. These are some of the best programmers at the time, right? Employed at major companies. Professional programmers had a couple of hours to convert the description into a programming language of their choice. High-level pseudocode was fine. 90% of the programmers found bugs in their programs, and I wasn't always convinced of the correctness of the code in which no bugs were found. Okay, so that's a quote from John Bentley. And the problem he's assigning is binary search, right? It's one of the simplest algorithms. And when I joined Adobe, I worked with this guy. His name's Mark Hamburg. This was Mark Hamburg's statement. I want to hire the other 10%. Right? Mark read this article. I believe you read it actually in the book, in John Bentley's book on Programming Pearls. And he wrote his own statement, problem statement, for a binary search. And to this day, if you want to hire into the Photoshop team, you are handed this sheet of paper that has a description of binary search. You're told, take it home, write a piece of code, any language you want, pseudocode is fine, to solve this problem. Okay, it's a very precise statement of a particular binary search. Bring us back the code and a description, it doesn't have to be a formal proof, as to why you believe your code to be correct, a correct solution to the problem as stated. Okay. When I joined the Photoshop team, I had to take this test. Right? After I joined the Photoshop team, we hired other people, and I administered this test. So I got to review and see other people's feedback. So I was very familiar with the problem of binary search at this point in time. To this day, I would say it is still more than 90% of the people to whom we administer this test. And at the point that we administer it, it means you've already been through interviews and the team says, yeah, you know, this could be a good candidate. Give them the take-home test. Right? 90% of the people who make it to that level for whom we take the take-home test fail. Utterly. Okay. The other thing that was going on at this time, if we're back now in 93, 94, well, 94, so is working on Photoshop. Photoshop is written in C++ at this point in time. It was originally written in Object Pascal, but it's been ported to C++ at this point. And there's a buzz forming around STL. A little bit of a buzz in the industry, right? It's getting a little press. You can read articles on STL. And I think this is interesting. I would like to incorporate STL into Photoshop. But Photoshop at the time had its own exception handling system based off of set jump and long jump. Right? There weren't any C++ compilers at the time that actually implemented exceptions. So Photoshop had its own way of dealing with exceptions. And so if we were going to incorporate a new library into Photoshop, you had to review all of the code and figure out, well, what happens if you ran out of memory, right? We're running on machines that didn't have a VM system. They're 32-bit machines. We're dealing with very large documents in Photoshop. So having operator new actually throw one of our exceptions was common, right? And having to recover from that and continue was common. So if you were going to pull in a new library, you had to go and look at all the places where an error or an exception could happen, and we had to retrofit that to work with our exception handling system so that we could use it so that Photoshop could continue to be robust. So for some context, this is John Bentley's solution to binary search. This is written, or this is translated by me to C++. In John's article, he puts it in pseudocode. I thought it was more readable for folks here if I put it into C++. But this is a faithful translation from his solution for the binary search problem. And John also published a version of this code in C, and this is almost identical to his version in C. So this is a faithful rendition here. Okay, so this is John's binary search. So one of the first things we find, okay, is that if our range is empty, we're just going to return -1. So we need kind of a flag symbol to specify what we're going to return. There's a problem with this line of code. Anybody know what the problem is with this line of code? This line of code can overflow, right? Right. So this line of code basically cuts your possible range for your binary search in half, because this can overflow. Okay. There's a few things going on here. One is there's an unnecessary comparison. We have 2 comparisons going on each time around our binary search. Right. The other thing that's going to happen here is we're only going to return if we actually find the item. Okay. If we don't find the item, we're going to end up here. Right. Right. So we've got a number of small little problems with this, right? And this line right here is also a possible underflow. We can end up at -1 here. So I'm reading the STL code, and this is the version of binary search that I find in the STL code. So This version of binary search would pass with flying colors the Photoshop take-home test. This is a beautiful implementation of binary search. Right? First thing is the interface is not just dealing with searching for integers, it's an abstracted interface, so it's to search on anything. It's also written in terms of a half-open interval instead of a closed interval, which eliminates a bunch of the boundary cases. It is carefully constructed so that your integers never overflow. There's a single comparison that happens each time around the loop. And if the item is not found, instead of returning -1, it returns useful information, which is the position at which you would insert the item. Okay. So I read that piece of code and I'm like, wow, this is a beautiful piece of code, right? But it's not just that piece of code. It's every single algorithm in STL. They're all short like that. They're all very concise like that. And they all go together like little puzzle pieces. And you have very complicated algorithms like stable sort, right, which was rated at the time by Don Knuth as being a level 50, which is a nearly impossible exercise to do an in situ stable sort with the right time complexity. And Alex has a beautiful implementation of that inside of the STL, right? Most of the programmers whose code I review can't write a correct binary search, much less a clean and beautiful one like this. Alex didn't just write a clean and beautiful binary search. He wrote an entire library of algorithms that fit together that are all clean and beautiful, right? It was an amazing piece of work that Alex and Meng put together. It really was. So that brings us all the way up to 1998. And this happened, right? C++ gets standardized, ISO standard, and part of that standardization includes STL. So this library that looks like no other library at the time actually makes it through the standards committee, right? Against a lot of odds, right? Because if you guys all know, I think if you have a new idea, the first response from anybody, any engineering team, is to say like, whoa, that's new, that's weird. No, okay? So partially because of Alex's friendship with Bjarne, STL actually makes it into the standard, right? That was a tremendous piece of work that basically all came together in 1 year to put STL together. That's a picture of the folks on the C++ Standards Committee at the time, a fairly small group compared to the Standards Committee today. The same year, there was also a conference known as the International Seminar of Generic Programming, right? So now they're getting a little buzz around generic programming. And this paper was written that I wanted to call out. This is Dave Abrahams. He was one of the principals on Boost for a long time. He also kind of left the C++ community a few years ago to work on Swift. He also is the person who started BoostCon, which is now C++ Now, the conference in Aspen. So Dave published this paper, Exception Safety in Generic Components. Okay. I think this is a very important paper. For me, this was, I thought, a brilliant little piece of work. Right? I'm somebody who took STL and had to retrofit it to work with Photoshop's exception handling, and I did it very ad hoc. I did not do a good job on it. Right? This paper basically breaks down what guarantees you need to provide on objects in the event of an exception. And a lot of people view this paper as being just about exception handling, but it's not just about exception handling, right? The same argument holds for what the state your objects should be in the event of an error, right? So if you say, well, we don't use exception handling, you still want to read this paper because it tells you what happens when your function returns an error, what state should you leave your objects in, right? So another paper that was published at the same conference was this paper, Fundamentals of Generic Programming. This was written by James Dennert and Alex Stepanov. This is here. This paper is important for two reasons. The first is this. This is the first place where the term concepts appears in print. Right? So this actually happens right after STL is standardized. We call the set of axioms satisfied by a data type and a set of operations on it a concept. Right? Prior to that, Alex used more mathematical terms like an algebraic structure or multi-sorted algebras to describe concepts. Right? The reason why Alex was unhappy with those terms is that in mathematics, you don't have complexity. Okay? And Alex thought that a fundamental piece of programming was the complexity of an operation, and that the complexity should be part of the axioms of the operation that describe it. So part of the mathematical structure is the complexity of the operations. So he wanted a new term and decided to go with concept. So this is where the term concept comes from. So if you think about it in terms of iterators, right, what we know of as iterators in STL, iterators are a mathematical theory. They have a set of axioms that apply to them. The only difference between a bidirectional iterator and a random access iterator, or even a forward iterator and a random access iterator, is the complexity of increment and decrement. Right? So the complexity has to be part of the axioms that define the theory, that define the structure, define the concept in C++ terms. The other part of that paper was this. Since we wish to extend the semantics as well as syntax from built-in types to user types, we introduced the idea of a regular type. Right, regular type. This is the first place where the term regular type came into print, which matches the built-in semantics, thereby making our user-defined types behave like built-in types as well. So what that also means is that the STL algorithms that you can use with all the built-in types, you can use with your own types. And that was part of the STL to begin with. Right? This is just where it was formalized and written down. And it's a very important idea. Right? Before this, if you had a list of objects, you probably had to write your object to inherit from list node. Right? Or to be somehow a list node, right? A data structure would be relatively intrusive. You wanted to put things into a dynamic array, you had to inherit from some root T object, right? That had the necessary method so that you could put your object into an array. You wanted to put an integer into your array, you had to package it into one of these objects that you could put into your array, right? It's called boxing. You still see things like that if you've ever done any programming in languages like Java or Objective-C, this notion of box types, and this primary difference between user-defined types and the built-in types. Right? STL did away with that with the notion of a regular type. So that brings us up to 2002. So in 2002, Alex is VP and Chief Scientist at Compaq at this point. He described his job as basically being in charge of mergers and acquisitions. And at this time, Compaq was also being acquired by HP. So that acquisition was in process. Now, Alex had a friend, Larry Musser. Larry worked at Adobe in Adobe's Advanced Technology Lab, in the research lab, which is where I was at the time. So I was working in the same organization as Larry. But Larry also worked with Alex at Bell Labs, so they knew each other and they were friends. And Larry invited Alex to Adobe and said, hey, come give a talk about your work on STL. So Alex came to Adobe and gave a talk. And I attended that talk. After the talk, Alex and I ended up chatting for a bit and then going up to my office and chatting some more, and I think we chatted for 3 or 4 hours. At the end of our conversation, Alex said, you know, I really wish that I could go and do this again, that I could just be an engineer again and not be a VP anymore. And I said, well, you know, why don't you, right? What's stopping you? About 2 weeks later, Alex gave me a call and said, you know, I gave that some thought. Are there any positions open at Adobe? So we managed to find a position. Unfortunately, I couldn't hire Alex at the time into my organization, but there was a position at Adobe that Alex was hired into. Alex was hired at Adobe. Within about a year or so, he was fired from Adobe. I had to scramble a bit, pull a few strings, and managed to get him hired back on the same day that he was fired from Adobe. Condition of me bringing Alex back was that I manage him. So that was the creation of Adobe Software Technology Lab, which I managed for about 8 years. We spun out of Adobe's research organization. At the peak, there were 5 members of the Software Technology Lab. So myself, Alex Stepanov, Paul McJones, Matt Marcus, and Foster Brereton. Foster and I still work together on Photoshop today. So while we're running the Software Technology Lab, this is a picture of somebody named Greg Gilly. He was my boss at the time. He's also the person who was nice enough to hire Alex back. So Alex was complaining to Greg as we're running the Software Technology Lab and Alex is teaching classes that nobody in the industry really knows what Alex was trying to do with generic programming. And Greg tells Alex, well, of course nobody knew what you were trying to do with generic programming. You never really wrote it down, right? And so that led to an effort for Alex to write a book. So this was the first manuscript of the book. This is Notes on the Foundations of Programming by Alex Stepanov and Matt Marcus. The book was never completed. That's a picture of Matt and his son Kai. So this book also went by the name Programming as Mathematics. It was written over the course of, I don't know, a year and a half, 2 years. And Alex and Matt had a disagreement about the direction of the book, and the collaboration kind of ended, and the work on the book stopped, and it was scrapped. Somewhat unfortunate. It's still a pretty nice piece of work. You can find it online. I'll have links at the end here. But that led to another collaboration, which in 2009 meant we published out of the Software Technology Lab this book, Elements of Programming. So this is Alex Stepanov, and well, the picture here is Paul McJones. So written by Alex Stepanov and Paul McJones. That's Paul, member of the team. So this is a very different book than the PAM book. So the PAM book was a much easier read. This book, largely influenced by Paul, was to take Alex's idea and put them down just in terms of a nice, clean math book, right? So if you read Elements of Programming, it reads as a math book. How many people here have read Elements of Programming? A few people, so you should get a copy. Paul's a great computer scientist in his own right. He actually worked with John Backus at Bell Labs, at IBM on System R. This is a picture of John Backus, right, going all the way back to that 1977 paper. Right, this is John, Turing Award winner, and he came to visit us in the Software Technology Lab. So quite the honor. And I got to sit in on a meeting where Alex explained generic programming to John Backus, who, remember, his Turing Award lecture was on freeing us from the von Neumann machine in architecture, and centered around functional programming. And John was very impressed and agreed that when he had done FP, he always knew, right, he had also done Fortran. He always knew that at some point he needed to figure out how to work mutation into functional programming. And one view of generic programming is that generic programming is functional programming with a well-defined way to handle mutation, right? So that can be one view that you can have of generic programming. And John Backus was going to write the foreword for Elements of Programming. Unfortunately, he passed away before that happened. Now, if you've read Elements of Programming, the term generic programming never appears in it. And that's because Alex thought that he had lost control of the term generic programming, and that generic programming had come to mean effectively metaprogramming. It had come to be associated with C++ templates and not associated with the underlying mathematics and the underlying algorithms, right? So Alex was trying to put a little distance between himself and that term. This is the first partition algorithm that appears inside of elements of programming. So compared to the Ada code, you can see now this is much shorter. But I wanted to call out this line. This appears in all the code, right? This is a require statement. So, right, this code, which is in the book, this is back in 2009, is not really quite C++, right? So, in fact, it's written in this language that's defined in an appendix of the book. It's 7 pages in the back of the book. And I wrote the appendix and did the language design with Bjarne Strustrup for the book. The syntax for the language is described in terms of EBNF. So now we get John Backus influence a little back in here. And it's described at the outset as being a subset of C++, but clearly with the requires clause, it's not quite a subset of C++. And so you see within the grammar here that we can have constrained templates. Now within the book, concepts are described, but they're not described within the programming language. Concepts within the book are described in terms of mathematics. Right now, a concept is a relationship, and for any relationship, there's a corresponding predicate. So we wrote the code in terms of the corresponding predicate, and we wrote the relationships in terms of mathematics in the book. Which brings us up to 2006. Or back to 2006, so a little before this. Some of these ideas were not completely new. There were efforts to get concepts into the C++ programming language. In fact, there were 2 competing factions to do this, one from Indiana University and one from Texas A&M. Bjarne Strustrup was at Texas A&M. Andrew Lumsdaine was at Indiana University. 2 competing proposals to incorporate concepts into the C++ programming language. C++ Standards Committee said, you know, you guys need to figure out one proposal. So they created this document, which was a unified proposal. It was written by Doug Greger, who did GCC implementation of Concept C++ and became one of the designers on the Swift programming language. Jaakko Järve, who did lambdas for C++ and lambdas for the Boost library. Jeremy Seek, who was largely responsible for the Boost Graph library. Gabriel Das Rees, who's now working on modules within C++. He left Texas A&M, and now he's at Microsoft. And Andrew Lumsdaine, who's done a lot of work both on Boost Graph library. He was a professor at Indiana University. And his group was responsible for high-performance computing at Indiana University. So they wrote this unified proposal for concepts, which brings us up to C++ 11. And this happened. Nothing, right? C++ 11 shipped without concepts. The unified proposal failed. It was a bit of a mishmash, kind of things glommed together. The Standards Committee said, you know, this really doesn't make sense. Now we have these 2 proposals of which we didn't have a lot of experience with either of them. We certainly have no experience with the 2 of them combined. The committee rejected it. So in 2012, licking wounds a little bit, Alex had left Adobe and gone to A9, which is a subsidiary of Amazon. And Alex hosted a workshop that led to this paper. This is known as the Palo Alto workshop. And this is referred to as the Palo Alto Report. The co-author on this with Bjarne Strustrup is Andrew Sutton. You might know Andrew Sutton. He gives a lot of talks on Concepts Light for C++ 20. So in the Palo Alto Report, what we argued, you know, Alex, Paul, and myself, was that in EOP, in Elements of Programming, we had demonstrated that that just having this notion of a light version of concepts, of having constrained templates, was incredibly useful, and that we could describe STL in terms of requires clauses instead of having full definitions of concepts inside the language, and that provided a huge amount of benefit and clarity to the algorithms, and that subset was worth pursuing. So that became known as Concepts Light. 2015, Alex published this paper with Daniel Rose. This is a great book. This is a great book that traces the history of algorithms and ties generic programming into the history of mathematics. Kind of presents the worldview that generic programming is an extension of mathematical algorithm evolution over time, right? And it traces some very fundamental algorithms from as early as the Pythagoreans all the way through modern time. So this is a bit of a history book, a bit of a textbook, much lighter read than Elements of Programming. So go read it. You also see here that Alex is reclaiming the term generic programming. And that's largely because of his co-author, Daniel Rose, who convinced him, that said, no, you still own the term, we should use it, let's tie it back in. So in 2016, Alex retired. This is his retirement party. And you can see most of the people in this talk are there. The two people who I haven't mentioned yet are Ryan Ernst, that is that person, and Anil, that's Anil. Ryan and Anil collaborated with Alex on information retrieval and SIMD-based decoding work for doing search. So they're not quite in the generic programming vein, but they're also Alex collaborators. Which brings us to the future, 2020. This is the working draft standard for C++ in 2020. And what you see here is very similar to what we had in EOP, right? A syntax for adding constraints to templates, right? This is Concepts Light. And so hopefully, this time, Concepts actually makes it in to the language. So I want to leave you off with a closing quote here. Generic programming is about abstracting and classifying algorithms and data structures. That's what generic programming is about. It gets its inspiration from Knuth and not from type theory. Its goal is the incremental construction of systematic catalogs of useful, efficient, and abstract algorithms and data structures. The sentence is very important. This is what Alex was trying to do. He created STL as a starting point of what he thought should eventually be a very large library of data structures and algorithms that would all work together, written in a generic form, right? So that's what he was going after. STL isn't intended to be the beginning and the end of generic programming. It is intended to be an example of how the industry should move forward, and that we should work on building large libraries of this form. And such an undertaking is still a dream. So that's my closing quote. I've included some references here. The slides will be available, so we'll send out a link, so don't try to copy that all down. There is one thing I'm going to call out in the references here, which is I threw a video. The video goes actually back to 2003 here. I posted a good, very nice version of this, thanks to a friend of mine, Scott Boyd, on YouTube. So if you get some time, watch the video. It's a lecture that Alex did in 2003 on the history of greatest common measure, greatest common divisor, for the last 2,500 years, and talking about how each mathematician during that history made the algorithm for greatest common measure more generic through time. And so it's a very fascinating talk and gives you the other 2,500-year history of generic programming. So that's my talk. Thank you. I think I'm about 3 minutes over.
One thing that's missing is huge thanks, Sean Parent.
I don't know if we have time for any questions.
Yes, absolutely. I think so.
Okay.
Questions, please.
Any questions?
Can't see any. Hit me on 3. 1. You know. Oh, thank you.
All right, thanks. So I was unable to skip opportunity to ask you a question.
Sure.
So what's your opinion about the difference between generic and meta programming in few words?
The difference between generic and metaprogramming. So metaprogramming is a mechanism, right, for writing code in terms of classes. Generic programming, right, you can write generic programming even with concrete types. The idea with generic programming is what you're trying to do is describe software in terms of the underlying axioms, okay, and the rules that govern it, and that describes what algorithms you can have from that set of axioms, right? So you can write generic code potentially in C, and assembly language. It's also a lens through which you can evaluate a piece of code. Right? So it's taking those fundamental laws, right? And the more constraints you have, the more axioms you add to a type, the fewer models you have. So at some point, if you add like one more axiom, you end up with there's only one model, there's only one concrete type. So that's what I mean when I say that I can write generic code and end up with concrete algorithms. Right? So it's very much an approach to trying to discover the rules that govern the algorithms and then expressing the algorithm in terms of those rules, which is different than just writing code in terms of templates.
Thank you.
Helps.
One more question. You do it like this. And then I come up to you and give you the mic and you ask the question. It's a very simple algorithm.
Yeah. Yeah, if there's anything you guys want to chat about, I'm here for the rest of the day, too, for the rest of the
Okay,
conference.
I've got one, if I may.
Sure.
Were you successful in managing Alex? And if so, what did you do to manage him?
So I was. I have the distinction of managing Alex longer than any other boss in his entire career. Yes, Alex is a very opinionated individual. As a manager, I've managed lots of teams. I managed Photoshop for a while. I've always viewed management, the task of a manager is to try to create an environment within which your employees can thrive, right? Management is less about being the boss and telling people about what to do, and it is more about removing obstacles so that your people can be productive, right? And steering them a little bit so that you end up at the goal you want to get to. But if you tell somebody go this direction, they might take one step in that direction, begrudgingly. But if you say, where do you want to go, right? You might be able to bend that and get 10 steps. It's maybe not quite the direction you want, but it's in the general direction of where you want. So that's always been my approach to management. So, with Alex, I think it worked very well. And we're still good friends to this day.
Well, congratulations. Ladies and gentlemen, 40 years of history, about 2 years of future, and the one and only Sean Parent. And now I'd like you to flex your muscle, or both of them, and do it properly. Sean Parent!